you want to know how to do something in the most efficient way. That's really what we study, except of course this is vaguely phrased. Does anybody have examples of what you need to do to do something most efficiently? So one example is how much fuel to put in an airplane. That's an optimization question, right? For example, if you put too much fuel in the airplane, it's very heavy, and therefore it wastes more fuel, right? If you put too little, it's not enough to carry you through the journey. So, what shape is most efficient to contain a certain amount of volume? For example, why planets are spheres. So there are many types of important problems that say there is something about how light travels through a medium, right? So light tries to travel through a medium so that it gets out in the quickest way possible. So let's consider very easy examples of how optimization might work. The optimization we're dealing with is actually just still toy optimization, very simple type of problems compared to what you face out there. So example, so suppose you have two numbers, x, or let's say two positive numbers, whose sum is 10. What should be those numbers? So that their product is as big as possible. So just asking such questions doesn't mean that there is an answer. Maybe there is no choice of two numbers that will give the biggest product. Maybe if you can always pick pairs of numbers that give you a bigger product and a bigger product and a bigger product. Okay? So solution. Let's try to analyze this, this problem. So what we have is, we have two numbers, x and y. We don't know what they are. We are free to pick any two numbers, right? They have to be positive, and that means bigger than 0. Now there is a constraint. Now what's the constraint? I mean, I cannot pick any two numbers. Can I pick the numbers 11 and 7? No, because why? The sum has to be 10, right? So that's what I call constraint. So I'm not allowed to pick any two numbers. So those two numbers, x and y, have a relationship between them. What's the relationship? Exactly. X plus y equal to 10. That's the constraint. Okay? And we want maximal product if exists. We don't know that there is such a thing, right? Maybe this question has no solution. So the product P is what? We have x plus y is 10. What's the product? xy. Now notice that we have that this constraint is equivalent to y equal to 10 minus x, correct? So in fact, if I know one of the numbers, I right away know the other. So really, I can define a function p of x. Right? Selecting one number determines the second automatically. So p of x is equal to x times what y is, which is 10 minus x. Okay? So we have this and notice that x, where is x? X is, let's say, we make it bigger than or equal to 0 to make it closed, and less than or equal to 10. Now we have a function that is a polynomial, therefore continuous function, and we have a closed bounded interval. Now for every continuous function on a closed bounded interval, we are guaranteed to have both maximum and minimum, absolute maximum and minimum. Now, the way to find this maximum and minimum is, now that we have a formula, we can pretend that we are looking at its graph, but our eyes are closed. And therefore, we have this ski method. Remember, ski-shoes method approach, that I'm going to try to imagine that I draw this graph for this function p, and I'm going to ski on this graph, and I'm going to just feel if my ski shoes are pointing up or pointing down. What am I interested in finding? When my ski shoes are doing what? I'm searching, remember, for a maximum. So my ski shoes should do what? Well, if they are pointing up, it means that this point at which I'm staying is not maximal. Because that means if I just slide a little bit farther, I'm going to be higher. Do you see that geometrically, right? So where am I looking? So you understand the idea, right? So I'm trying to find the maximum of this function, and I translate that to an attempt to picture the graph. But I'm too lazy or too ignorant to know how to draw this graph, let's say. Right? Maybe you right away recognize this graph, and you can do it. So what do I do? Close your eyes and fall asleep. No? So, first of all, by extreme, value theorem, both absolute max and abs min must exist since P is continuous on closed and bounded interval. Okay? That's the very first observation. In fact, for this function, maybe too strong to make. I mean, it's just a statement that is true for much more scary functions. So I have this formula P of x, which I can write as 10x minus x squared. I'm searching for the maximum again. I imagine then in searching for the maximum that I'm skiing on the graph. My ski shoes are doing what when I'm located at either a maximum or minimum? If my ski shoes are pointing up at a point x, that means I'm still climbing. If they are pointing down, that means I'm descending. The maximum might have been behind me. So where should the ski shoes be pointing? How should they be pointing if I'm at a maximum? Flat. Flat? Does flat mean maximum? So I take P prime x, and I get 10 minus 2x. And I search when this is equal to 0. 0 means that I am at a critical number, that I am somewhere, my skis are horizontal. So if my skis are horizontal, I don't know what's happening. I might be just at some saddle point, so it might be neither max nor min. It might be a minimum if I am at a valley. It might be a maximum, right? So I solve, and what do I obtain? I obtain x is equal to what? 5. X equal to 5. Now, again, for this easy problem, it's almost redundant, but I want to determine if at 5 I have maximum or minimum. So here is 5. At 5, my derivative is 0. What happens if I select a value bigger than 5? You look at this equation. Yes, if I select a value bigger than, careful. If I select, first of all, a value below 5. If it's below 5, then 2 times that value is smaller than 10. And therefore, this is positive. Agreed? What about here? Negative. So this is what? Max. So in fact, then if x is equal to 5, I just measure what is P of 5. So P of 5 is, using this equation, is 5 times 10 minus 5, which is 25. Other values of interest are, in fact, they are pretty redundant. X equal to 0. We're not allowed this condition. I just made this x equals 0 in order to make this a closed and bounded interval, in order to ensure that we have both max and min. So then we have P of 0 is 0, and P of 10 is also 0. Now the fact that P of 0 is 0 and P of 10 is 0, in fact, implies that we must have, you see that this graph is differentiable, so that must be the absolute maximum. X equals 5 gives absolute maximum, where P of 5 is 25. Hence, we must have y, which is equal to 10 minus 5, also 5. We have the pair of numbers is 5, 5. That give us maximum. There is no pair of numbers that give us the minimum, notice, right? So the fact is that if I don't allow 0 or 10, I can make the product of those numbers as small as I like. Okay? So this is the easiest possible optimization problem. Let's consider other examples. So you understand, I mean, the idea of why we found when the derivative is equal to 0. Right? It's a very simple idea. Derivative equal to 0, critical point. That means that my sleds are horizontal. If they are horizontal, it could be a maximum, it could be a minimum, it could be neither. But that's just a point of interest. That's why we call it a critical point. So suppose that farmer has (2,400 feet of fencing). And I'm a little lazy to write the full problem. So imagine that he needs to enclose a portion of land. And the portion of land is bounded by one side here, it's river. And the portion of land that he wants to enclose is a rectangle where there is no need to fence the river. Right? So the animals are not going to escape through the river. So they are to be enclosed in this amount of fence. Right? Now you see what you have a choice. You have a choice of whether to make this enclosure very thin but long, or to make it more stocky. So we want to maximize area. This is A. Maximize enclosed area. First, we want to label what are we allowed to change here. So what can be changed here? The length and the width, right? So let's call this x and this y. Okay? They are the same here. So we have one x and the two y's have to be the same. So first we have constraint. And what's the constraint?
X plus 2y.
Exactly. X plus 2y is 2,400. And then what is area? Exactly. It's x times y. And that's what we want to make as large as possible. So because we have x plus 2y equals to this number, we can in fact predict, as soon as we know one of the dimensions, we know the other, right? So we can solve for y, for example, or for x. Let's solve for x, actually. So we have that x is equal to 2400 minus 2y. And therefore, we have that area as a function of y is 2400 minus 2y multiplied by y. Agreed? Now, continue with this problem. I want you to tell me what's the max and min. But you see, it's very similar to the problem we just had before. Almost exactly alike. So first, to see if this problem even has solution, what's the possibilities for y? What's the smallest y can be? 0. Of course, we know that 0 is not a realistic value, right? If y is 0, we just have a fence that is right at the river. It's not really enclosing any area. And the other possibility is for y to be too large, and that is, well, even less, because, well, 24, that's fine, but you can say less, because y should be 1200, right? Agreed? So y is between 0 and 1200. Now, having stated that, can we be sure that there is a maximum? Can we be sure that there is, in fact, the best possible arrangement of the fence? Yes. Now, mathematically, because of the extreme value theorem, this is continuous. It's a polynomial, in fact, right? So it's continuous, and this is a closed bounded interval. Y is between 0 and 1200, so that assures us that we can find both max and min. Minimum is uninteresting, it's 0. It's when y is 0 or y 1200. The minimum enclosed area is 0. The maximum enclosed area is what we want to find. So then we can just take a of y and multiply the y through. Yes, there is a y. Good. And now, and this is what I really would like you to tell me. Why do I take the derivative? How does derivative help me? To find where the slope is 0. Why do I care to find when the slope is 0? Why does it find the absolute maximum? Right. So you see, what you do is a little bit of imagination. So what we have is now, the problem is purely mathematical. A of y is some curve that I can draw in the x, in the two-dimensional plane. Right? So if I make the horizontal axis y and the vertical axis z, so that would be a curve, in fact, a parabola. Right? It's a simple curve. But let's say we don't know that. So we imagine that we are skating blindly on that curve, and the skating is basically at the points where we find that the derivative is positive. That means we can go a little higher and get bigger values. And we find that if the derivative is negative, we can go backwards and be a little higher. But in the places where the derivative is 0, that might be a place where we are at a maximum. It also might be a place where we're at a minimum, because maybe after the 0 we go up, and before the 0 we also go up. Okay? So we find this derivative, and we get 2400 minus 4y, and we set this equal to 0. And so y is equal to 600, right? 600. That corresponds to where a prime is 0. Now what happens if I select values below 600? Then 2400 minus this number is positive. And if I select after 600, we find that it's negative. So 600 is a what? Maximum. Now, since this is differentiable everywhere, we know that has to be the absolute maximum, correct? So the corresponding value of x is 12. Okay, so we have the pair 1200, 600 dimension of enclosure. Okay, or I don't know how you say it. 12 by 600, right? Okay. So here is one problem that is somewhat similar to the problem faced by soft drinks companies. So example is, you have a can. And the way you build this can and this can is constructed out of the lid and bottom and a flat sheet that you curve into a cylinder. Okay, so it's this plus that plus that. So this can is supposed to hold one liter of liquid. So find dimensions that minimize the amount of material used. In other words, dimensions that minimize the total surface area. Question makes sense, right? So you want to construct a can, you have to, it has to enclose 1 liter. Now you don't want to waste too much material in it. So material is proportional to surface area. So find the dimensions of the surface area that make the amount of material minimal. So first of all, we want to know how we can control the amount of material in the can. So if I look in the can, I have the control of how wide it is, and that's controlled by the radius here, right? And I also have control of how tall the can is, and that's controlled by h. Now, if this is a cylinder of radius r and h, what can you say about it? If you cut it out and unfold it, it becomes a flat sheet of paper. That's if you cut here. It becomes a flat sheet of paper. What is this dimension here? H. What is this dimension here? Sorry? Careful. Right? So this dimension here is just the unfolded circle. So that would be what? 2 pi r. So the dimensions here are 2 pi r. So the total area used here is 2 pi r h. Right? And then we have the two lids. So we have the lids are of radius r. So what we have is the area of those lids is pi r squared, and because we have two of them, it's 2. Right? So what we have is that the surface area of the can is 2 pi r squared. This corresponds to lid, so top and bottom. It's top and bottom of can plus 2 pi RH, which is the cylinder. Agreed? So that is our equation of the surface. Notice there are two variables. There is r and there is h. We must eliminate them somehow. So how do we eliminate it? The volume has to be 1 liter. So how do I calculate the volume of the can? Constraint is that 1, which is volume of can, is equal to what?
Pi r squared h?
Yes, pi r squared h. So easiest is to eliminate h, right? So the implications is that h is equal to 1 divided by pi r squared. So therefore we have that the surface as a function of r is 2 pi r squared plus 2 pi r and times h, which is divided by pi r squared, which simplifies to 2 pi r squared plus 2 over r. Now this function is rational. You agree? It's not a polynomial. We have division by r. So in this case, how big can r be? So clearly r equals 0 is not reasonable, right? So we are going to control it by the radius. We can make the r as small as we want. And so what we have is r is going to be bigger than 0 and smaller than infinity. So what can we say about, does the extreme value theorem apply? No, it does not, right? Extreme value theorem and that means that our problem might have no solution, right? In other words, there might not be a best shape for the can. Yes?
Why isn't it a
Well, it's not an easy theorem. You need analysis to prove it, but there is a statement that if you take any continuous function whatsoever, right, and if it's defined on a closed bounded interval, then it has max and min. Now we have a continuous function here in the interval from 0 to infinity. The problem is this interval is not what you call compact. It's not bounded interval. Because its length is infinity, yes. And also because, let's say, it's not closed, it does not contain the borders. It doesn't contain 0. It doesn't infinity, obviously. Well, it doesn't contain the borders. Okay? So just a priori, without extra analysis, we don't understand that, we don't know that this problem has a solution, right? So still, we'll try to do the derivative test, see what we find, right? This function, wherever it's defined, it's differentiable, right? In the interval from 0 to infinity, this is a continuous differentiable function. And therefore, if we have a maximum or a minimum, it will occur only at a point where the derivative is 0. Correct? So what we do is we take s prime of r. S prime of r is 4 pi r minus 2 over r squared. And we set this equal to 0. Since r cannot ever be negative or 0, we can multiply this by r, and what we get is 4 pi r squared. Actually, pardon, I need to multiply by r squared, so it would be 4 pi r cubed. It's 4 pi r cubed minus 2 equal to 0. You see what I did? I multiplied by r squared. To make it simpler, I say to just either you bring everything under a common denominator, it ends up being the same, right? So you end up being required to solve this polynomial. And that means that r is equal to 2 divided by 4 pi to the cube root. Which is, I guess, simplified 1 over 2 pi to the cube root. Okay? You with me, guys? So now let's draw the number line for the derivative. So this is S prime. On this number line, I place somewhere the number 1 over 2 pi to the cube root. Can you see from this equation what would happen? So this is where S prime is 0. What would happen? I cannot select r equals 0. So what happens if I select a number r smaller? If it's so you look into this equation. If it's smaller, it's -2, so it would be in fact negative. Right? I mean, instead of kind of doing this calculation, I noticed that it's the same as checking this equation, 4 pi r cubed -2. So if the thing that solves it to be 0 is this, now I select something smaller, then 2 is bigger than this number. You understand? I don't do any calculations. I just think this quantity, if I plug instead of r, will make this equation 0. Now, if I make this quantity smaller, then this will be smaller than 2, and therefore negative. Correct?
If you put 0 in for r, it would be -2.
So if it's 0 for r, it would be -2, which, by the way, of course, we cannot put 0 in r because the original equation, the reason I was able to multiply by r squared and make those equivalent, they're equivalent as long as r is not 0. But you're absolutely right? So, I mean, I can, instead of looking at this more complicated equation, I can look at this equation provided I remember that, that r is not 0. But the analysis is all the same here. So it's negative. What happens if I pass beyond this number, 1 over 2 pi cube root? I become positive. Okay? So this is -0, positive. What did I find? Minimum. Now notice that, in fact, this derivative indicates that if I were to draw the curve, approximately, right? I mean, this first derivative test gives me a very rough sketch of how the curve looks like. Here, what happens with r? If this is r, this is s, what happens? So first of all, notice that here is the number 1 over 2 pi to the cube root. Now, if r is too small, so here it's just at the maximum is some point I can evaluate it by plugging this number into the original formula, into this formula, I can evaluate what this number will be. Now, if r is too little, 2 over r will be huge. This thing will be huge, right? So what I have is, if I get below this point, I'm decreasing. So the graph is like this. By the way, asymptotic to the s-axis, and afterwards it's again increasing, and eventually it becomes asymptotic to the quadratic function. So here it looks like 1 over r roughly, and here it would start looking like the quadratic function goes to infinity. So that's the minimum amount of radius I can use. You see what I can do? In theory, I can make this can to be very flat to the ground with a very big lid, huge lid. So it's like imagine almost like a huge disk on the ground, right? And there is no amount of how wasteful I can be with the material. So if you want to embezzle, you can use this graph. You can understand that you can just build cans that contain 1 liter, but that are huge and waste a lot of material. But the least amount of material wasted is if r is equal to 1 over 2 pi to the cube root. Right? That gives you the dimension r. From the dimension r, you can obtain what h is, right?
That's
We-
not the absolute minimum because we don't have extreme value.
It's the absolute minimum, but without the extreme value theorem, we realize that. It's because you see what happens if you look at this analysis. This is the only place where the derivative is 0. The derivative is negative below this value and positive afterwards. So that means that we are between 0 and 1 over 2 pi to the cube root. We are descending down, and then we are ascending again.
So it is the absolute.
So this is the absolute minimum, but not by the extreme value theorem, which doesn't apply. Notice that this is a slightly more difficult problem, and by the way, not realistic, right? Notice that in a real soda can, there must be some reinforcements at the edges, right? Real soda can will not have those dimensions. Actually, a much more difficult problem. Example. So this is like two-dimensional simplified version of astrophysics. So imagine that we have a comet. And the comet is, so the sun is somewhere here. The comet is going to fly in a parabolic path. So here is a comet, and somewhere here, so its path is determined to be given by the equation y squared equal to 2x. Y squared equal to 2x. And somewhere here, is planet Earth. And it's located at position 1, 4 on the graph, right? So the problem is to find the closest distance from the comet to planet Earth. How close is it going to pass? Find closest to comet. Comet is spelled like that or 2 M's? I don't remember. Correct? Okay. All right. So what does it mean? It means that this comet in general is in position xy. And then we just take the point 1, 4 and we measure this distance, right? So let's call this distance L. Now, what is L in terms of a formula? So we have two coordinates. We have coordinate x, y. That's changing, right? So the comet is going to be in different places. You can see by the picture, closest distance will be somewhere here, right?
So is it right at the slope?
Slope is just, when we have a right triangle, there are actually non-calculus methods of finding this answer. But using calculus, what do you do? First, you just measure length, right? So you measure the distance formula. So L, and by the way, there is a nice trick here. So let's actually say F, which is equal to the distance squared. F equals to the distance squared is going to be x minus 1 squared plus y minus 4 squared. Okay. Now there is a nice trick. So this distance is always positive, right? So you might try to find the minimal distance L, but that would involve another root. And that involves harder derivatives, more complicated derivatives. But here we use the idea that L is positive. So suppose I'm holding two numbers, and I'm going to show you the square of those numbers. So suppose that the square of the number I'm holding in my left hand is bigger than the square of the number I'm holding in my right hand, and I know that both numbers are positive. What can you say about the relationship between the number in this hand and the number in this hand? In particular, suppose that I have a number whose square is 100, and here I have a number whose square is 25. Which number is bigger? Not exponentially, quadratically bigger, right? Right. But the numbers themselves. All I care about is that square functions preserve distances. They preserve, sorry, not distances. They preserve relative sizes, right? If I have a number a squared and a number b squared, and I find that a squared is bigger than b squared, that means that a is bigger than b. Do you understand? As long as those numbers are positive, of course. Now the distance L is positive, so that's a trick that we're using here. You understand that other than that, you would have had to calculate the root. And roots are not very easy to take their derivatives. It's more involved. So then we are going to notice that we have that y squared is equal to 2x. So I can replace y by so I can say that well, actually, yes. Let's so that it's because I don't want to take square roots. I'm going to say that x is equal to y squared over 2. Okay. So in this formula, I'm going to have it as a function of y. F of y is y squared over 2 minus 1 squared plus y minus 4 squared. Okay. Now this is a polynomial in y. Therefore, if we have a maximum, if we have a minimum, those happen when the derivative is 0. So I calculate f prime of y. So the derivative of this part is 2 y squared over 2 minus 1 times 2y over 2 plus twice y minus 4 And this is what I want to solve when this is equal to 0. So in other words, sorry? This is chain rule, yes. I mean, I'm taking the derivative of the outer function, which is just dropping down. And then we have this inner function, and then times the derivative of the inner function, which is 2y over 2. Right, and the derivative of y minus 4 is 1 with respect to y, right? So what we have here is this 2. So we have here 2y, just to cross out, 2y, y squared over 2 minus 1 plus 2 y minus 4 equal to 0. So then we can multiply it out. And what we get is this times that is y cubed minus 2y plus 2y minus 8. Right? So notice it's a cubic equation, and only because of luck we have those two parts cross out. So that makes it a simple cubic equation. If we had a y, that would be something you would have had a lot of difficulties with. So this is simply y cubed minus 8, and I solve when this is equal to 0. So how do I factor y cubed minus 8? That's y. How do we factor this? 2 times what? Y squared plus
4y.
Plus, so no, it's 1 power drop, so it's 2y plus 4. Okay, equals 0. Now you can rest assured that this does not have solutions, right? You can, if you want to verify that, but you see this is y squared plus 2y. How should I say that? Here, if you want to, you can write y minus 2. And what you see here in parentheses, this is the same as y squared plus 2y plus 1 plus 3. Right? Let me write it actually elsewhere where you can see it. So, but whatever remains is going to be a reducible quadratic. So what you have here is y minus 2. Here in parentheses you have y squared plus 2y plus 1 plus 3, which is y minus 3. Y minus 3, not 2, right? No, y minus 2 it was. Y minus 2. And here I have a perfect square y plus 1 squared plus 3. So what I have here in parentheses never equals 0. The implication is that the solution is when y equals to 2. That's the only 0 I have.
What's the stopping from saying y cubed equals 8 and then just taking their cube?
Nothing does, in fact. You're right. I factored that. You might have as well. It might have been even a smarter thing. You're right, absolutely right. Smarter to do than what I'm doing. I just saw difference of cubes, possibly because I thought, well, I need to remind you of the difference of cubes. Possibly because I just, did not think simply, right? So you're right. Even better than that, y is equal to 2 because you just take the cube root. There is only one thing. Good. So y equals 2. So does this 2 correspond to a minimum? Well, geometrically, you can see by just looking at this graph, do you see that there should be a minimum, right? You can see that if you're traveling by the parabola, you're moving like this. So the minimum is somewhere here. And then your distance is going to increase. So geometrically, it's evident that that where we find the derivative, we found only one derivative where it's 0. That has to be the minimum. But without intuition, let's see if we want to do that. Yeah, we can do that. So what we have is the derivative is f prime of y is simply y cubed minus 8. So if I draw and put 2, that's where f prime is 0. Now if I select value below 2, notice y is never smaller than no, should I say that? So if I select yeah, that's the derivative. That's fine. So if I select y smaller than 2, what can you say about the derivative?
It's smaller.
So the derivative, what's the size?
Smaller than 0 is negative.
Smaller than 0. Wonderful. So the derivative is negative. After 2, just we plug a value bigger than 2 here. So it's going to be positive. So 2 corresponds to, it's negative, then so it's local. So it's a local mean, which has to be absolute mean. You see why it's absolute mean? Because we found the derivative, and it's just only at 1.0. Below 2, it's negative. That means that it's decreasing all the time to 2, and then increasing after 2. So just by analyzing the behavior of the derivatives, you know it has to be absolute minimum. You see, simply what this is saying is that if I draw the curve f, the curve f is decreasing until it reaches to 2, and then it begins to increase after 2. So that has to be absolute minimum. Make sense? Again, as you can see by the picture, the y can range from anywhere, from minus infinity to infinity. So in fact, the extreme value theorem cannot be applied.
So maybe it's a question. Do you add do you plug in 1 and 4?
What do I do with 1, 4? I measure the distance L between 1 and 4. Right? So and I find that I want to know closest approach. So I want to know the values x and y. So I just found the y coordinate. Y coordinate is equal to 2 when the comet is closest to planet Earth. Planet Earth in this graph is located at coordinates 1, 4. Doing all this process told me that the y coordinate of the closest point on the parabola to the point 1, 4 has y coordinate equal to 2. Make sense? The x coordinate can be obtained from here. Just solve this equation. solve this equation here. So we now know the closest point. So closest point corresponds to the coordinates y equal to 2. What's x? X is going to be 2 squared over 2, which is what? Which is again 2. Make sense? Notice the trick we employed. Instead of taking the derivative of the actual distance, we took the derivative of distance squared. That's to simplify formulas. Okay? We just replaced the original function that we need to optimize by another one which has the same location over which it has max and min. Not the same max and min, but the same location, the same values x and y give a maximum and minimum or minimum for f as they do for L. Yes?
Why did you ignore y plus 1? I don't know if you
Ignored y plus 1?
Yeah.
Where is y plus 1?
Oh, you found derivatives?
This never equals 0. And by the way, there was a suggestion which is better. Just look at this. I say I did this. If you'd like, ignore this. Ignore this factoring of cubes. Just look here. Much simpler. Y is equal to 2. One other thing, maybe there is an I factor, that is you know that if you use complex numbers, that's not the only solution, right? The solution y cubed equal to 8, it has 3 solutions. If you use complex numbers. If you don't use complex numbers, it has only 1. Yes. So for example, what is the cube root of 1? You think 1. That's only one solution. There are 2 others.
What are the other two?
Huh?
What are they?
Cube root of 1. Here. So if you take cube root of 1, that splits into, so basically what you do is it splits into 3 numbers. One of them is 1. The other number is e to the power of 2 pi I divided by 3. And the other one is e to the 4 pi I divided by 3, which if you look at them, it's connected to trigonometry. So that would be minus. So the number is minus 1/2 plus I, which is the square root of minus 1, times root 3 over 2. And the other one is minus 1/2 minus I square root of 3 over 2.
What's
I is root of minus 1. The reason is actually you can think of the number system as a machine. So there is a particular. So what you do when you do operations on the number line. You have another razor. That's again, I'm deviating from the topic, but just in case somebody would eventually be interested. So the number line, just the one you're familiar with, the real number line is a machine, right? And what this machine is doing is what the way you can think of addition is this. So for example, +1. So imagine that you have two number lines, one sliding on top of another, right? So +1 means that you slide the top number line 1 unit ahead. So if this is 0, so you slide it 1 unit ahead. That's +1. +2, slide it 2 units up. So you have two infinite lines, and they can slide, right? What is multiplication by -1? Multiplication by -1, you take this top line and you rotate it to the back. So notice that that means that, let's say, the number, this is the number, let's say if this is 0, this is the number 2. So the number 2 is carried to, so if you rotate it, should I say, not rotate it, you just flip it, sorry, even better, right? You flip it, it's carried to -2, it's carried to -2. So what you do is when you multiply by -1, you flip it like this. Okay? And when you multiply the number line by, let's say, 5, what it does, it stretches the top number line. Okay? That's that's pretty much the operations that you're capable of doing with real numbers. Now, in complex numbers are two-dimensional numbers. So instead of having a line, you have actually a plane, and on top of it there is another suspended plane. And what you can do is you can move this plane not just like this, not plus minus, but you can move it to the sides, right? And you can rotate it. So you have more possibilities. You see, you can actually rotate the plane. Okay? And what else you can do? You can take one plane and flip it. Take this plane and flip it. So the machine that describes this set of motions is the complex numbers. And what they are useful for is when you study geometry, two-dimensional geometry can be completely described by those motions. And of course stretching, right? So like you stretch the number line, you can take the top plane and you can stretch it. So this is what you do with geometry, because imagine that on one of these pieces of paper, you draw a triangle and you want to show congruence. Basically, you want to show congruence. What it means is that there is a triangle here and there is a triangle somewhere there. So what you do is you copy this triangle onto the top plane, you move it to the right place, you rotate it, and you stretch it. Okay? So complex numbers are more sophisticated. They are able to express Euclidean geometry and even higher geometry. Yeah.
Doesn't that have to do with like alternate universes or something?
Alternate universe.
Different planes.
Well, but what do you mean by alternate universe?
No alternative.
Oh, yeah, I understand. But what? So you use them for many things. For most of which, I mean, are not in my current database of knowledge, right? But one interesting thing is let's say the way you can think of the universe. You can think of this as bounded. So the way the one model for which you can think of it as bounded is, imagine that if you cannot imagine three-dimensional bound universe, you can imagine definitely what happens with 2 dimensions. So what you have is an infinite plane, and the infinite plane is just a reflection of the light that comes from the north. So it's like this. So in fact, when you're traveling in this direction at a constant speed, what's actually happening is you're moving up the sphere, and you're moving slower and slower and slower. So never reaching the point at infinity if you travel at constant speed. Okay? So you have those ideas. So that the universe is both infinite and actually the full infinite bounded universe is completely engulfed in a small tiny sphere. Right? And you can just make a three-dimensional analog of that. So interesting things, I guess, I hope. Right? But we're in calculus, which is... Yeah.
No, because I learned this in like math, like core math. It was like in core class or something.
In core class, what did you learn?
You just
Complex
were
numbers.
talking about four-dimensional, and then they were talking about like alternate universes.
No, I mean, if you study, there are a lot of interesting things. They are very difficult, but a lot of interesting things. So one thing is those numbers are used in electricity theory, in the theory of electricity and magnetism, but I don't know the theory of electricity and magnetism yet. So I cannot describe how it's used exactly. But that's one of the main applications that I know of complex analysis. Also, it helps with certain questions. I mean, my friend, he had to study physical chemistry, and he was asking me some questions about that stuff because there were integrals. We're going to learn about integrals that he had to solve in physical chemistry. So those numbers help you solve certain things that you cannot do with real numbers. All right. Over the summer, of course, you'll have the time to read the physics book that I have on my website, right? So it goes up to relativity theory, I think. So it's a pretty good book. Huh? No, I didn't write books. I'm too lazy for that. I have lecture notes for all sorts of things, and right, but not a book yet. No. All right, so let's do a few more questions here. You're going to continue. I mean, I'm telling you all the stuff. You're going to continue in math, some of you, right? Yeah. All right, so here is a problem. So this is like a toy GPS problem, right? So when you use your GPS, you want to find the quickest route to your destination. So this is a toy GPS problem. That GPS is a good example of optimization, by the way. So you have a river, and the river is 3 kilometers. So it's 3 kilometers wide. You are in point A. Across from you in the river is the point C. And you want to get to point B. Now the distance from point C to point B on land is 8 kilometers. Okay, so you have several options. So you have you can take a boat, or basically swim. Let's call it swim. Swim speed is, let's see, six kilometer per hour. Or maybe not swim. Let's say you take a boat. You don't want to be wet, so let's call it row speed. That's how fast you can row the boat. Okay, so it's 6 kilometers per hour, and your walk speed, or you can run, is equal to 8. Kilometers per hour. So, problem. Find fastest route. It's T at the end, right? Route like this? Yeah. So what does it mean to find the fastest route? It means that you disembark somewhere at the point D. This is one possible path, right? So you see, what sort of possible paths can you have? You can either take the boat to point C and then run. So you use the boat for the least amount of time, right? You are slower on the boat. But on the other hand, you can use the boat to go diagonally across, and maybe that will save time, and then run. You see, so the two extreme situations is you use the boat only to cross the river, or where you use the boat all the way through to point B. Make sense? So, solution. So let's call the distance traveled by boat, let's call it x. And let's call the distance traveled by land y. Okay? So solution, we need to minimize, so length of journey, or duration of journey better said, not the length, duration of journey. Is t. It's the total amount of time you traveled, and it's equal to t on the boat plus t when you were running. Do you agree? So some amount of the trip you were rowing the boat, some amount of the trip you were running. So far make sense? Now, if I travel the distance of x on the boat, what's t of b in terms of x? In fact, that's why we're going to t of bx. So yeah, so that would be how much. Basically, it's at what time we traveled. So we know that tb. Let's do it like this. 1 second, right? So we know that tb, the amount of time times the speed times 6, should equal x. You agree? The amount of time it takes to travel this distance times the speed will equal to distance traveled, right? So that means that tb of x is x divided by 6. Does it make sense? Yeah? All right. And tb of y, or tr of y, is y divided by 8, right? So our total trip is t equal to x over 6 plus y over 8. So we need to replace it in terms of one variable. So it's just in terms of, let's say, x. So, or in terms of y, right? So if this is y, then this leg of journey is 8 minus y. All right? And we observe the relationship here that 8 minus y squared plus 3 squared is equal to x squared. So let's put everything in terms of y. So we have t of y is equal to 8 minus y squared plus 9 square root of that divided by 6 plus y divided by 8, where y, this y could be smallest is 0. When y is 0, that means I travel directly from A to B. And when y is equal to 8, that means that that I run longest, right? So y is between 0 and 8. Correct? So then all that's, by the way, so in this case, do we have a minimal journey? Look at this expression. Do we have a minimum? Yes. It's a continuous function. It's algebraic. And we have a closed bounded interval. So we have a minimum. So what we do is we take the derivative. So t prime of y will be one half one second. So it would be 1/2 parentheses 8 minus y squared plus 9 to the power of minus 1/2.
What happens to 6?
I didn't yet finish, right? So 6 is there, sure. It's all divided by 6 times the derivative here. So it would be minus, so it would be times 2 8 minus y times minus 1. And all of this thing is over 6 plus derivative of y is just 1, so it's just 1 over 8. Right, so this 1/2, this 2 cross out. So what we have is we have minus 8 minus y divided by this thing, the square root of 8 minus y squared plus 9. And there is a 6 here. Plus 1 over 8. And we want this to equal 0. And so what you do is you cross multiply. So what you have is so what you have is 8 minus y equals to 6 root 8 minus y squared plus 9. So divide this. So what you have is 8 divided by 2 is 4 over 3. 8 minus y equal to square root of 8 minus y squared plus 9. Then you square both sides. What you have is 16 over 9, 8 minus y squared equals 8 minus y squared plus 9. Wait a few moments if you want. And so I can move this across. So what we have is 16 minus 9 over 9 times 8 minus y squared is equal to 9. So where is it? So what is it? This is 7 over 9, right? So 7 over 9, 8 minus y squared is 9. So now we take the square root. Y, remember, is positive, so take the square root. So we have root of 7 over 3 times 8 minus y is equal to 3. So this equation is now simple to solve, right? So you can figure out what y is, just move things about. So that means that 8 minus y is equal to 9 over square root of 7, and 8 minus 9 over the square root of 7 is equal to y. So 8 times root of 7 minus 9 divided by root 7 is my y. So this is one possibility. The other possibility is y equal to 0 that you need to check. And the last possibility is y equals to 8 that you need to check. One of them has to be the minimum. Okay? All right. So